Hello everybody. In this video we're going to talk about chain rule, which is a very uh, powerful tool to calculate partial derivatives. It's from section 14.4. So we're going to divide the chain rule into several cases, and we start with the easiest one. So we first look at this theorem 5 and try to apply this to the first example in this section, and then we're going to do even more complicated things, and we try to find out a pattern which avoid memorizing a formula. All right, so suppose W is f of xy, which is differentiable, and x is a function of t, which we call it x equals x of t. So you can think of x as a variable for this f, but x itself is a function of t, and y also depends on t. So we say y of t. So all those three functions are differentiable. Then the composition of w, which is equal to f of xt y of t, is differentiable function of t. In other words, w, obviously from here we can see w is a function. Depends on what t you're given. So if I'm giving you t, a number, then you can plug in, and we can find x of t and y of t separately, and then put it into f and find w. So eventually, so at the beginning you give one number t, then eventually you get an output w. So w is a function of t, but it's provided by composition with two variable function and single variable functions. So w equals f of xt yt is differentiable function of t, and whenever you need to find out dw dt, because w is a function of t, you can compute dw dt, the derivative with respect to t. Then the chain rule says it is partial f with respect to x times x prime t plus partial y prime t. Or you can rewrite this dw dt in terms of another notation, partial derivative notation, df dx or dx dt, df dy dy dt. If we use more convenient way, then we can just think of f is function w. So we can replace f by the variable w. So we think of w as a function. Then we can rewrite this as following. So dw dt, and we replace f by w. dw dy dy dt. So another way we can rewrite this one is following. So to memorize to prepare for even more complicated case, so we are going to try to find a pattern for this kind of chain rule. So w is a function of xy, and we can put this in the diagram. So I can think of w as a machine or function which depends on what variables you're feeding from x and y machine. So it's going this way. And then you're going to have output, which we call that w again. But sometimes we call this as f or g, h, it's fine, but we just, for simplicity, we just use those variables as functions. And what is x? X is a function, again, x is a function of t, and y is a function of t. So we can put this as following. They're coming from the same t value. So maybe for the first one, it's independent variable, so we can just put it as just t, and the last one is w. All right, then the question about this is the differentiation with respect to t. So our chain rule says it's supposed to be this. Or we can rewrite this as Wt equals, oh, this is not correct. This is Wx, partial x. And here, this is partial x. So we can rewrite this as Wx, xt, Wy, yt. That's another way, or simpler way. And the chain rule can be interpreted as a diagram which can be thought of Wt. When you think of Wt, when t change, how much W change? That's the differentiation. Then what you do is you're thinking of imagining you're starting from here, reaching out the destination W. So Wt, you start t, and then there are two ways. This is one route, and another path is coming from here. Then we need to calculate each link for its differentiation and put them together as a chain rule. So for this, the differentiation gives the rate of Wx. This gives xt. Then if you put them together, you need to multiply the ratio for the chain rule. Then that becomes Wx xt. So this upper link gives you one a part of the rate, and another part of the rate comes from the lower link. So this is Wy and Yt. That gives me the second part. And you need to put them together, take the total sum. That's the differentiation. Now we come to the next example. So W is given by xy, where x is cosine t, y is sine t. Find the derivative of t at pi over 2. So this is basically, this problem can be given in the calculus 1, something like we are given W as xy. X is indeed cosine t, y is sine t. And then find derivative of W, because W is a single variable function depending on t, and when t equals pi over 2. That's the same question. In other words, this problem is completely solvable in calculus 1. However, we're going to use different method using chain rule in multivariable calculus, which gives easier approach. I'm leaving this approach from calculus 1 for your own exercise and see if you can get the same answer. So we got, the problem is this. W is x and times y. X is cosine t, cosine t, and y is sine t. Now I want dw dt at t equals pi over 2. Then we know that, again, Wt is Wx, then xt, Wy, Yt. So w as a function x and y, partial derivative with respect to x, then y is frozen as a constant, so its coefficient, and xt. This is entirely from calculus 1. Cosine t prime is negative sine t. And now wy, so we look at w given by xy. So now y is activated, but x is frozen. So x is constant. So wy is x, and yt is cosine t. Now, now I want to look at t when pi over 2, then I need to replace that. So when I look at y is given here. Y, which is sine t. So y value at t equals pi over 2 means sine pi over 2. So this is sine pi over 2. And then negative sine pi over 2. And x is cosine t. So cosine and t is pi over 2 and cosine pi over 2. And that gives me cosine pi over 2 is 0 times 0, which is 0. And sine pi over 2 is 1 times negative 1, which is negative 1. All right, next we're going to look at slightly more complicated chain rule. However, we still have the same scenario, and as long as you have diagram, then you can correctly find the formula, and you don't have to memorize everything from this theorem. So we look at the structure. W is given by x, y, z. It depends on x, y, z. But x, y, z's are functions of t. Then what is the ratio or different derivative of w with respect to t? So when t change, then how w change? That's what it means. So there is a formula which comes from this diagram. Now we have w, which is fed by three variables x, y, z. And x, y, z are coming from this t, right? So basically this gives one path. Wx times xt gives me this part. And another thing is wy and yt gives me this part. And another possible, so the only difference from the theorem 5 is we have three intermediate variables instead of two. So that means we have another path going from t to w, which is wz and zt. Now if you put them together, add them together, we get this one. So if you like, you can write this as following. So wt equals wx xt plus wy yt plus wz zt. Now we use this formula and try to solve the next example, which is example 2. So w here is given by x, y, z variables, and x, y, z's are functions of t in different form, and I want to find what is derivative of w with respect to t at t equals 0. So we are using the chain rule, but with three intermediate variables, and my question is what is wt? Then we have wx xt, wy yt, and wz zt. As long as you have this diagram in your head, in your brain, then you're able to write this down immediately and then calculate. So each term goes to calculation of derivative, and wx is because w depends on three variables given by x, y, z. This is partial derivative with respect to x, and y, z's are constant, frozen. So that means z prime is 0, constant prime, and x, y is constant, so y is coefficient, and that means this is y. And xt, negative sine t. Now y is activated. Other things are frozen, so x, yt, we come here, sine t prime, which is cosine t, and wz. So this is constant now, z is activated. So constant prime is 0, and z prime, with respect to z, it's 1. So wz is 1, and z equals t prime is 1. And we want the value evaluated at t equals 0. That means sine 0 is 0, cosine 0 is 1. So you have to know what is x of 0. In other words, here, when you look at x formula, when t equals 0, cosine 0, which is 1. And 1 times 1, no matter what t is, it's just 1. So this is 0 plus x of 0 is 1 times cosine 0 is 1 plus the last one is just 1. So the answer is 2. Now I guess we can look at further and generalize any complicated structure as long as you have the idea of the chain rule. So now theorem 7 is w is still a function of three variables, x, y, z, but x, y, z's are functions of two variables, rs and rs and rs. Now, if we put them together, then w can be dependent to two variable r and s. So suppose you are given r and s as two numbers, then you can determine x, y, z first and put x, y, z inside of f, then you get w. Now our question, so w is a function of rs, two variable function. Then the question about derivative is partial derivative. What is partial derivative with respect to r, with respect to s? Now, for this problem, we have, of course, we have this complicated formula, which we are not going to memorize, but we have something in our, some picture in our mind. So we know that w is fed by xyz. So we put xyz here. All right, again, as a function, x itself depends on rs. So we have r and s. Then x depends on rs, and y is also depends on rs. That comes from this. We call that as h, but we don't have to write this down. And z is also depending on r and s. So when I want to compute dw with respect to r, then that means you're looking for the roots starting from r going to w. So there's three possible ways you can reach W from R. So this link, which means WX here, and XR. Maybe I can. So here's WX and here's XR. If you put them together, then we're having this one, WX XR. Now another way you can reach from R to W is going to be this link. And along this link, we have WY and YR. Put them together. Of course, first multiply together and put this as another another ratio. And then you can calculate the differentiation along these pairs. This is WZ and ZR. So multiply them together, this comes here. All right, WS is the same thing. So we can look at WS. If you're starting from S and going to W, then along the upper link, we have WX here. And along this XS, this is XS. And along this is, so we get this one, which is, I can write this WXXS. Now along the second route, this is WY and this is YS. WY and YS. And along the third line, this is WZ and ZS. So WZ plus Z, not plus ZS. All right, now we can see the next example. W is a function of three variables, and X is function of R and S, two variables. Y is also RS function. Z is just depending on R, but you can think of it, it's a function of R and S. It doesn't matter. Now, what is dWdr? So we're going to leave the second question, dWds, as our exercise. Then so let me first take another blank page. So when I look at WR, we can use that diagram, immediately look at WX XR plus WY YR plus WZ ZR. Now what is WX? WX, here only this is variable, other things are constant. Constant prime is 0, 1. Now when I look at XR, this is constant. You can think of R over 2. What is R over 2 derivative? Then this is 1/2, right? So R over S derivative, you can think of this as X equals 1 over S times R. This is constant because we are looking for derivative with respect to R. So X prime is 1 over S. Now WY. When I look at here, only this term matters for WY, which is 2 after derivative. And YR, here YR, only this term matters. That means 2R. Now we look at WZ. For WZ, when I look at here, only this term is Z term. So this is 2Z. And ZR, I'm looking here. This is easiest one, which is 2. Now, the answer is 1 over S plus 4R plus 4Z. Let me first put this. And there's no target point or limit point to evaluate. So then in that case, if possible, I'd like to write everything in terms of R and S. And Z is intermediate variable. I don't want to leave it in the middle. So 4R and 4 times Z is given by 2R from here. And then if I simplify, that gives me 12R plus 1 over S. All right. So we had 3 examples here. And from the simplest one to harder ones. Now I think you're ready to make a conclusion, which means you are able to generalize this idea to any complicated scenarios for chain rule. So suppose W is given by a function of many intermediate variables. By intermediate variables means those variables are indeed a function of other variables. So there could be many. So in that case, you are able to find, so eventually W is a function of those PQTs. Then you can ask WP, WQ, WT. Then we can always write the chain rule. And the way to do that, the correct form comes from the diagram. All right, that's pretty much everything, and we're going to stop here.